Hello, good morning. In the last lecture, we have discussed finite difference approximations to elliptic PDE, in particular Laplace equation. Of course, I have shown it for a Poisson equation as well. So, now the main crux of the problem is the system ultimately reduces to a sparse system of equations. So, now we must focus on few concepts on handling sparse systems. Okay. So, yesterday we discussed in the last lecture we discussed efficient way of storing sparse systems. So, now let us focus on the corresponding iterative methods. So, let us see how a general iterative method works out for solving A x equals to b, a kind of linear system of equations. Okay. So, the system under consideration is this, and we are aiming at solving this iteratively. So, we need to split something like this, where P is non-singular and of the same dimension as A. So, if you can do this, then what would happen? One can define an iterative scheme and x naught given. So, this kind of an iterative scheme can be defined. Okay. So, however, the question is whether any kind of P would do or P should have some specific structure. Okay. So, P demands the following properties. So, if we define this iterative scheme, and x 0 given P is supposed to have the following two important properties. So, one, say this is star must be solved reasonably easier. So, in some sense this must be solved with a little bit of less effort. Okay. Star must be solved reasonably easier, and 2. So, this kind of structure which supports this, that means relatively easier. Okay. So, possible structures are P is diagonal matrix or P is lower upper triangular. Okay. So, this if P has this structure, then one can expect that this system is relatively solvable easier way. Okay. Then the matrix must be a contraction mapping. So, as you can see, so here when we get such a structure, we ask for, since P is non singular, then we can write it I minus. Okay. So, therefore, this must be a contraction mapping, so that the method converges. So, in other words, this means, in other words, eigenvalues of this to lie in a unit circle. Okay. So, I am not discussing the complete theory, because you can see any book on linear algebra. Okay. So, this must be contract mapping, that means eigenvalues of this to lie in the unit circle. Okay. So, let us see a couple of methods where it has this kind of structure. Okay. So, let A be, so this is diagonal and this is lower, upper, triangular matrices. Okay. Now, if P equals to D, so then the method is called Gauss-Jacobi. If P equals to D plus L, then the method is called, so we see in detail anyway. Okay. So, if so when P is D, so the system under consideration is A x equals to B, and this we have split as and P we want to be D. Okay. So, therefore, the structure we would have is so A minus D would be the remaining I am sorry, this is this is D, therefore, A minus D will be L plus U. So, D inverse L plus U, okay. Of course, x not given. Okay. However, see we need convergence. So, this should not grow up. Okay. So, in order to have that, one remark is equations are to be rearranged to maximize D. So, maximize D means when I say elements of D. Okay. So, if you do that, then so this is minimum. Okay. So, this will ensure faster convergence. So, this is the structure of Jacobi. Then Gauss-Seidel so, this is a case where P is D plus L. Okay. So, this will converge provided the norm is less than 1. Okay. So, let us take some example. Okay. So, let us take an example. So, let us take this A, then rearranged by exchanging row 1 and 2, then say call A prime. So, this would be so you can see when we split this into D plus L plus U, D contains the larger elements, whereas here D contains 1 to 2, whereas here it is 2 3 2. Okay. So, this is what we mean maximizing D. Okay. Now, to compute eigenvalues of because this is for Jacobi. So, we need this matrix. Okay. So, to compute the eigenvalues of this, we need to solve okay. Since D is non singular, this amounts to okay. So, now for the present case for A prime. Okay. So, when A prime equals we have D is okay, and L U okay. So, now in this case so if we solve this okay. So, now please check 1 root lies in okay. So, this you can check and the other two are complex conjugates. Hence, all of them lie in unit circle. Hence, Gauss-Jacobi converges. Okay. So, this is important aspect. So, when you define any iterative method, the convergence is an important issue. Okay. So, in case of Gauss Jacobi, we have seen corresponding eigenvalues of this particular matrix. Okay. So, this particular combination they must lie within the unit circle. Okay. So, now there is another convergence criteria. So, that is diagonal dominance. So, this is n cross n matrix A is said to be diagonally dominant if the sum, when you say sum, modulus of all the off diagonal. So, all the off diagonal elements in any row obviously is less than the sum of the diagonal elements. Modulus of the sum of diagonal elements in that row. Okay. So, one property. So, for example, consider so if you read this, is said to be diagonal dominant if the sum of the modulus of all the off diagonal elements in any row. So, if you take for example, if you take row 1, sum of these two, okay, so is less than the modulus of the, sorry, there is no sum here because modulus of the diagonal elements in that row. So, these two together is less than this of diagonal. Suppose in this row modulus of this is 1, suppose there is 1 here. So, that will be 2. So, which is not less than. Okay. So, whereas here the diagonal is 4 and then in this row 3. So, it is less than 4. Suppose there is 5 here. So, we can get another matrix for example. So, this is 2 is strictly less than 3, 1 is strictly less than 2, 3 is strictly less than 4. So, strict. So, we can call it as in short strict DD. Suppose we can construct okay. Consider this. So, consider row 1, the diagonal element is this and the sum 4. So, which is not less than the diagonal element. Similarly, the modulus of the sum is 3, which is not less than. So, this is not. Okay. So, strict diagonal dominance means we have convergence. So, the property, one property, okay, if A is diagonally dominant, this implies U is a contraction mapping. Okay. So, as I mentioned, I am not giving much of theory, because this is required for the iterative methods Gauss Jacobi and Gauss Seidel. In particular, this is required for Gauss Seidel. Okay. So, those who are interested in theory, they are supposed to refer any book on linear algebra. Okay. So, now once it is diagonally dominant, this is contraction mapping, hence our Gauss Seidel method converges. Okay. Suppose you consider so this is consider 3, it is less than or equal to, in this case. Okay, it is equality, and this is the diagonal element. So, 3. So, here, so this is not diagonally dominant, okay, because equality holds here, right. So, therefore, we cannot use the other criterion. So, hence compute eigenvalues of okay. So, eigenvalues of that so, all of them are within the unit circle, hence Gauss Seidel method converges. Okay. So, for the iterative methods, both Gauss Jacobi and Gauss Seidel method, these convergence criteria are important. So, now let us see a more general Laplace equation. So, this is given with a Dirichlet condition, then if we approximate for this, so I minus 1 j. So, for this and this, from here we get I minus 1 j, then we need I plus 1 j, then from here I j minus 1, I j plus 1, then minus 2 I j minus 2 I j. So, this we get okay, plus from here A I j okay, then from here then from here okay. So, now clubbing the coefficients we get okay. what we have done, we have just clubbed the coefficients. So, u I minus 1 j coefficient, because 2 h. So, 2 goes there, then minus because of h 1 h goes there. So, 2 minus h a I j. Okay. So, for this then I j minus 1, we have I j minus 1. So, similarly 1 2 from here and then from here minus h b I j. So, similarly for remaining terms. Okay. So, now based on this, if we consider the corresponding iterative scheme, okay, if we consider the corresponding iterative scheme, one can show that strict diagonal dominance requires because this is the diagonal term coefficient of u I j. So, for strict this has to be greater than sum of the modulus of these numbers in that row. Okay. So, now a general case will be slightly difficult, but for small h, assuming this is not shooting up. Okay. So, the condition is a minus 2 h square c I j is greater than. Okay. So, this implies c I j is less than 0. So, which means c of x y is less than 0 in the region of okay. So, that means if you consider such a general elliptic equation and if you want to define a corresponding iterative scheme. So, then it converges provided C satisfies this condition. Okay. So, this is definitely a useful inference. Okay. So, now having defined the iterative schemes, let us work out couple of examples where the solution is based on one of those iterative schemes. Okay. So, let us proceed for the example. So, we want to solve Laplacian okay, and say h is 5. So, now the grid so 0 okay. So, correspondingly okay. So, now I 0, 1, 2, 3 and j 0, 1, 2, 3. Okay. So, now the boundary u of x 0 is 0. So, right, then u of x 15 is 0. So, y equal to 0 and y equal to 15. Okay. Then x equals to 0 and here okay. Now, what are the unknowns? Unknowns u 1, u 2, u 3, u 4. So, these are the unknowns. So, now consider the discretized equation. So, this is a discretized equation. Now, if we run this equation at this point, it expects this and this. Okay. So, instead of writing with two indices, we have discussed in the last class one method of renaming, okay, a method of enumeration. So, according to that this will be u 1, u 2, u 3, u 4. Okay. So, now if we see, for example, this corresponds to u 1 corresponds to I equal to 1, j equal to 1. So, I will show in one case with the two indices. So, then we switch over. So, for example, I equal to 1, j equal to 1. So, we have star at I equal to 1, j equal to 1 will be u 2 1, u 0 1, so according to our notation u 1 1 is u 1. Okay. So, then 1 0 will be this, right. So, it asks for this point, this point, this point and this point, which are nothing but these 4. Okay. So, when I switch over to the other notation, simply it will ask for, you see, the value here, which is, so the value here. Okay. So, the value here is on this boundary it is 5. So, 5, okay, and inconsistent with this u 2 1 first. So, let me write down u 2 1 is nothing but u 2, u 0 1, 0 1 is this 1 2, that is u 3 and 1 0. So, that is this number. So, which is 0 minus 4 u 1. Okay. So, what I am trying to do is, if we run here, we need u 2 plus the value here which is 5 plus u 3 plus the value here which is 0, okay, minus 4 u 1, right. So, we do this way, right. So, it is slightly narrow, the earlier one. So, let me write down. Okay. So, in this case 0, 5, 15, 20, right. So, now this is u 1, u 2, u 3, u 4. Okay. So, now the boundary here u equals to 0. So, here u equals to 50 and here u equals to 0 and here u equals to 5. So, now the given equation we run at u 1. So, point 1. So, this is point 1, P 1, P 2, P 3, P 4. Okay. So, at point 1 if you run the equation we get u 2 plus this value 5 plus u 3 plus this value which is 0 minus 4 u 1 equals to 0. Next we run the equation at point 2. So, when we run the equation here we get this value plus this value. So, this value is 50 and this is u 1, then u 4, then value here is 0 minus 4 u 2. Now, at point 3. So, instead of what I am trying to do, instead of following from this, we know when we use at a particular point it needs 4 neighbors. So, I am just working out based on that. Now, at point 3 if you run it asks for this value plus this value. So, this is u 4 plus this value is 5, then the top value is 0, then u 1 minus 4 u 3. Similarly, point 4. So, this value is 50 and this is u 3, top value is 0 and bottom is u 2 minus 4 u 4 equal to 0. Okay. So, this reduces to minus 4 u 1 plus u 2 plus u 3 is minus 5. Then second equation u 1 minus 4 u 2 plus u 4 is minus 50. Third equation u 1 minus 4 u 3 plus u 4, then fourth equation u 2 plus u 3. Okay. So, we get this. So, now we need from here we define the iterative scheme as follows. So, u 1 is okay. You may realize when we put u 4. So, that is different. So, u 1 is done, then u 2 is okay plus 25 by 2. Similarly, Okay. So, this is iterative scheme. So, we are ready to consider either Gauss Jacobi or Gauss Seidel. Okay. So, let us start the computation. So, now we need any initial guess. Okay. So, we need any initial guess. So, let me write down say we start from 0 as initial guess, then so we have u 1 equals u 2 plus u 3 by 4 and u 2 is okay. So, now let us Gauss Jacobi. Okay. So, now in this we define, so we are ready to compute. Okay. So, u 1 1 equals, so u 2 0, u 3 0. So, therefore, 5 by 4. Okay. Then u 2 1. So, these are 0, 25 by 2, then u 3 we get this. Then Gauss Jacobi, as you know, once we get at next level we use them to compute further. So, this will be u 2 1 plus u 3 1 by 4 plus 5 by 4. So, this will be u 2 1 u 3 1 plus 5 4. So, this comes out to be 18.75 by 4. So, you can compute roughly. Okay. So, then u 2 2. So, u 1 1 u 4 1 by 4. So, this will be u 1 1 u 4 1 plus 50 whole by 4. So, this is 50 by 4. So, this will be 63.75 by 4. So, this is okay. Then u 3 1 so u 1 u 4. So, the same. So, this would be u 1 u 4 1. let me check whether I am making a mistake, because u 1 is u 2, u 1 is u 2 plus u 3. So, I have used correct ones 12.5 and 1.25, yeah, and 5. So, this is fine, because this turns out to be 12, 17, 18, 18 point. Okay. Then u 1, u 4. So, u 1, u 4. So, this is 13.75 and 50. So, 63. So, that is this. Then u 3 is u 1 plus u 4. So, u 1 plus u 4. So, 13.75 plus 18 point. So, it is same. So, this is same as 4.68. Then u 4 1. So, this is u 2 u 3. Okay. So, I am not, because you can compute u 2 u 3. So, these are 12.5 plus, so 13.75 plus 50. Okay. So, 13 point plus 50. So, this will be okay. So, this is up to 2 iterations. So, these are up to 2 iterations, right. Then let us try one more iteration, then we compare with Gauss Seidel, okay. Or we can try Gauss Seidel straight away. So, then now, so we have, so we need these values, u 1 is u 2 plus u 3 by 4, u 2 is so better we write 50 by 4. Okay. So, with 0 0 0, so when these are zeros, we get u 1 is 5 by 4. So, which is 1.25. Now, as you know, having obtained u 1 at the next level, we must use that to compute u 2. So, therefore, u 2 1 would be u 1 1, u 4 0, okay, and we have u 1 okay. So, that is how we have computed this. Then this will be, so this is 0, so this 50 by 4, okay. So, this will be so this is 51, so 51.25 by 4, so it is roughly 12.81. Then u 3 1, you can see we have computed. So, this also latest value we have to take. So, this would be okay. So, roughly this, then u 4 1. So, we have computed u 2 1 and u 3 1. So, we must use them. So, u 2 1 is 12.81, u 3 1 so this is roughly 51, 63, 64.31 by 4. So, this is okay. So, if you look at it, 1 point initial 1.25, 1.25, 12.5, 12.5, the later. So, now here second level we got first level itself 1.25, 1.56, 12.16. So, next iteration we have to use these values and compute. Okay. So, you can see, so for example, I do one value. So, u 1 2 is u 2 1 plus u 3 1 plus 5 by 4. So, u 2 1 is 12.1. So, u 3 1 1.56 plus 5. Okay. So, if there is a mistake, kindly correct it. Okay. It is only dictates the method. Okay. So, this is 6, 18. So, this is roughly 19 point. So, roughly this much. Okay. So, you can see which is Gauss-Jacobi is 4.68 and this is 4.89. So, that means calculation is correct. So, it is closely. So, however, you can see we are updating the latest values. In u 2 you would realize the benefit of that. So, this is supposed to converge faster. Okay. So, then having discussed Gauss-Jacobi and Gauss-Seidel, let us wind up this session with successive over relaxation. Okay. So, this is popularly known as SOR. So, convergence can be improved So, what we do, we add and subtract u I j k for this. So, then readjust. So, hope you are able to recall why we are putting k plus 1, because this is we are computing I past values, we should use the latest. So, this is nothing but residual. Okay. So, residual is a kind of adjustment, and further the more general method is defined as we add a relaxation parameter okay. So, this is in general for optimal convergence, it lies within this. Okay. So, lies within this. Okay. So, this is a little faster compared to other iterative methods. Okay. So, as you can see, the numerator goes to 0 as the method converges, okay, because this is nothing but the discretization of the Laplace equation. Okay. So, these are the iterative methods, because it is worth spending on iterative methods. The reason is straightforward, as I mentioned. For Laplace case, because of the second order approximations for the second derivatives, the neighbors are diagonal, right. So, you have one above and one below, one left, one right. So, therefore, what would happen, the tridiagonal structure is lost, hence the system is sparse. Therefore, you need definitely you need better solvers for these sparse systems, and hence instead of simple Gaussian elimination, we propose Gauss-Jacobi, Gauss-Seidel or successive over relaxation. Okay. So, in the coming classes we will see maybe some examples where derivative boundary conditions are also involved. Until then, thank you.